Hello everyone, my name is Van Nguyen. This is a joint work between ECCV system and the UIT machine learning group. And today I'm going to talk about our work, SEN. In the past few years, many approaches to few-shot classification have been proposed. This approach can be roughly categorized into 5 main categories: learning to fine-tune, sequence-based, generative modeling-based, distant metric learning-based, and semi-supervised approach. Among these categories, distant metric learning-based approach, for which prototypical networks are the most granular example, are typically preferred because of their simplicity and effectiveness. This is an illustration of a prototypical network. The basic idea of this approach is to learn a nonlinear mapping of the input into an embedding space. In this space, a metric distance is defined which maps similar examples close to each other. Dissimilar examples are mapped to distant locations relative to each other, so that a query example can be classified by, for example, using nearest neighbor methods. One of the most commonly used distant metrics in this high-dimensional embedding space is the Euclidean distance combined with the softmax function. However, even though the softmax is known to work well for closest classification problems, it has been shown not to be discriminative enough in problems where there are only a few labels relative to the numbers of classes. This has given rise to alternative loss formulations with improved discriminative ability, where high-dimensional features have been normalized explicitly to lie on a hypersphere via direct L2 normalization. However, direct L2 normalization leads to a non-convex loss formulation, which typically results in local minima generated by the loss function itself. In this paper, with the aim of performing short feature normalization while preserving the convexity and the simplicity of the loss function, we equip prototypical networks with a novel dissimilarity measure, SEN, particularly suited to enable discriminative feature normalization for few-shot learning without any direct normalization. We call this resulting model SEN PN. The SEN is a combination of the Euclidean distance and the norm distance. We propose a special balancing hyperparameter that is positive for the correct prototype and negative for the incorrect prototypes. This special balancing hyperparameter allows the SEN to be a norm equalizers in both cases, the correct prototype and the incorrect prototypes. This is the grading contribution with respect to correct prototype. It consists of two parts. The first part is an attractor that pulls example to its correct prototype. The second part is a norm equalizer that forces example to have the same norm as its prototype. In other words, the norm equalizer forces example of the same class to have the same norm. This is the gradient contribution with respect to the incorrect prototypes. It also consists of two parts. The first part is a repeller that pushes examples away from incorrect prototypes, and the second part is a norm equalizer. Originally, the second part forces examples of different classes to have different norms. However, since we use a negative epsilon to inverse its effect, this part now acts as a norm equalizer, which forces example to have the same norm as incorrect prototypes. In other words, this part forces examples of different class to also have the same norm. This analysis shows that SEN indeed explicitly forces all embedding to have the same norm during training, which enables the resulting SEN PN to generate a more robust embedding space. With this minimal but important modification, the SEN PN outperforms the original prototypical network by a considerable margin and demonstrates good performance on mini ImageNet and OmniClass datasets with no additional parameters as well as negligible computational overhead. As can be seen from Figure 1 and Table 1 here, SEN consistently outperforms the Euclidean distance in prototypical networks with different embedding sizes as well as different embedding networks. To investigate the effectiveness and behavior of the proposed SEN Dissimilarity Measure, we conduct several ablation studies. First, we compare again the prototypical network trained with the Euclidean distance and the prototypical network trained with the SEN Dissimilarity Measure. As can be seen from table 2 here, SEN PN outperforms prototypical network on all three datasets, OmniCloud, Mini-ImageNet, and FC100. We project embeddings produced by the two models to 2D space using PCA and visualize the outputs. It can be seen from figure 2 here. Our proposed SEN Dissimilarity Measure both forces the prototype to lie on a scale unit hypersphere and keep them well separated. We plot the norm of embeddings produced by the two models. As can be seen from figure 3, the norm of embeddings produced by the prototypical network varies a lot, while the norm of embedding produced by the SEN PN has a very consistent value. This confirms that SEN encourages all embedding to have the same norm during training. In order to demonstrate the effects of the hyperparameter epsilon, we train the SEN PN with different values of epsilon. The result illustrates that the accuracy increased initially at the negative epsilon decrease. However, it decreased slightly as the negative epsilon decreased further. With the n-way few-shot classification task, there is one correct prototype, but n-1 incorrect prototypes for each query example. So we use a small negative epsilon to mitigate the imbalance problem during training. Specifically, epsilon p equal 1 and a small epsilon n allow the training to focus more on forcing example of the same class to have the same norm in the beginning of the training. The focus is then gradually shifted towards forcing examples of different classes to also have the same norm. We evaluate the possibilities of combining the proposed SEN Dissimilarity Measure with all the distance functions such as the Euclidean distance and the cosine distance in training prototypical networks. As can be seen from table 3 here, the model trained with the SEN achieves the highest accuracy when tested with either the SEN or the cosine distance. This is because the SEN Dissimilarity Measure explicitly forces all embedding to have the same norm during training, and as a result, pulling the prototypes very close to the hypersphere. For data embedded on a hypersphere, the cosine distance is a natural measure of distance. We have also studied the behaviors of the proposed SEN in combination with other metric learning-based tasks, which are based on the idea of obtaining interclass separabilities and interclass compactness. To do this, we implement the well-known Sesame network and contrastive loss. We call these models the Sesame baseline. We augment it by replacing the Euclidean distance by our proposed SEN Dissimilarity Measure, which we call the Sesame SEN. We train the two models on the MNIST datasets for dimensionality reduction and clustering. As can be seen from figure 5, our proposed SEN both forces all embedding to lie on a scale unit hypersphere and keeps the embedding well separated. This suggests that the SEN can also be used beyond the fields of future learning, where distant metric learning is used and class memberships are available. In conclusion, in this paper, we propose a novel dissimilarity measure called SEN for distant metric learning-based future learning. The SEN is the combination of the Euclidean distance and the norm distance. We extend the prototypical network by replacing the Euclidean distance by SEN, which we refer to as SEN PN. With minimal modification, the SEN PN outperformed the original prototypical network by a considerable margin and demonstrate good performance across datasets. In addition, we provide analysis showing that the proposed SEN Dissimilarity Measure encouraged the embedding to have the same norm and enabled the SEN PN to generate a hyperspherical embedding space, which is a more compact embedding space than the Euclidean space. We experimentally showed that the proposed SEN Dissimilarity Measure consistently outperformed the Euclidean distance in prototypical network with different embedding sizes as well as different embedding networks. We also show that the SEN is an effective feature normalization technique not only for distant metric learning-based future learning with prototypical networks, but also potentially for more general tasks. Thank you for watching this video.